Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this video we cover all things Gen Chem related. On this video we'll be covering how we can determine if a metal is going to be magnetic or not based on the electron configuration. Let's get started. The magnetic properties associated with transition metals and different ions is based off of that spin that we see with the electrons that are found in the atoms. So atoms that have electron configurations that result in unpaired electrons will mean that the atom or ion will have an attraction to the magnetic field. This is going to be considered to be paramagnetic. Things that are paramagnetic are attracted to the magnetic field and would therefore have those magnetic properties associated with it. Electron configurations that result in all paired electrons across the board will not have that magnetic field created around it. And so we call those diamagnetic, which means they're slightly repelled from the magnetic field. And so we can use the orbital diagrams of these elements to predict whether or not a metal will be paramagnetic or have those magnetic properties or attracted to the magnetic field, or diamagnetic, which means it's slightly repelled by the magnetic field or no magnetic properties. And so what really helps us is not necessarily the electron configuration to help us figure this out, but really it's the orbital diagrams. Because when you look at the electron configurations, you may get slightly visually confused based on the fact that you're seeing even numbers, but not necessarily processing that there could still be unpaired spins. And so essentially, if you're going to have unpaired spins, the net result of any electron configuration or orbital diagram would be that all the sublevels are completely filled. There's no unfilled sublevel. In those cases, those are going to be diamagnetic. And so you can see in both the zinc and the Zn2 example, when we look at these, our S sublevel, our D sublevel is completely filled in the first example. And in the ion example, although our S sublevel is empty, it doesn't create any unpaired spins. So in this case, both the ion and the neutral species are completely filled or have no unpaired spins, and so they would be diamagnetic. So in that case, it would not be attracted to that magnetic field. But you could also have situations where the ion and the neutral species could be one or the other. And that's based off of, do we have unpaired spins that exist? And so in the example with silver or the silver ion that exists, we see in something like this, just silver, we have that electron configuration of 5s1, 4d10. So because we have that one unpaired spin in the s orbital, you would say that that is paramagnetic, and you would expect it to be attracted to a magnetic field. But in the silver plus ion, the cation version, we've now kicked out that one electron, and so the result is no unpaired spins, and we would say that it is diamagnetic. And then for the silver 2+ ions, we are now dipping into that D sublevel and creating one unpaired spin. So it too would be attracted to that magnetic field. All right, and so here we want to determine if iron and Fe3+ are paramagnetic or diamagnetic. Now, when we're dealing with this particular, defining this property, we can really just look at the shorthand configuration, because we know up until that point, the noble gas, everything's filled. And so we don't really need to worry about that. So with iron, the noble gas that precedes it is argon. And then if we continue on, we would say 4s2, 3d6. Now, don't let the fact that you see even numbers, shift your thinking and say, oh, this has to be completely filled. It must be, paired up. We know if we look at the orbital diagram for this, we have 4s up and down and 3d. Because of Hund's rule, when we put this in, remember, we're going up, 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 and then down. So we have those unpaired spins. The fact that we have those unpaired spins is going to be what dictates and leads to the fact that this indeed for iron is going to be considered to be paramagnetic, or meaning it would be attracted to the electron or the magnetic field. For the iron 3+ example, well, now it's the same, starting off with the same thing, argon, but now we've lost electrons in that s orbital, those two, and we're losing one from our d orbital. But if we look at that electron configuration, and maybe you don't even need if you look at the orbital diagram, you can see that in fact, you still have unpaired spins that exist. And so this also would be paramagnetic. So in both of these cases, we would expect them to have that attraction to the electron field. And so let us try some examples here. We want to determine if these are considered to be paramagnetic or diamagnetic. So if we find manganese on our charts, we have argon, followed by 4s2, 3d5, and immediately you can see you don't have a completely full sublevel. So therefore, you should automatically know that this is going to end up being paramagnetic. Okay, and again, that's because your d orbitals, you have those 5 unpaired spins that exist. For scandium 3+, so scandium 3+, we start with argon, and then we would have 4s2, 3d1 is the neutral. The cation situation, we now have lost the electrons that are found there. And so that would mean that we have completely filled shells here, which would mean that we are dealing with a diamagnetic species. And that means it's not attracted to the magnetic field. I hope this video helped you understand how to determine if you have a magnetic metal or not. Make sure you guys like, comment, and subscribe, and come back for more videos. See you guys soon. Have a great day. Bye-bye.